Okay, so we just talked about what a function is. We gave the definitions f of g of x is equal to x and g of f of x is equal to x. When both of these statements are satisfied, then we know that f and g are inverses. So the first type of problem that we will encounter here is to verify if two functions are inverses. Notice we're given two functions. A little bit later, I'll only give you one function and I'll ask you to get the second function. A lot of students confuse these two processes. So make sure that when you're given two functions, you follow the definition of a function, which is f of g of x has to be equal to x and g of f of x have to be equal to x. So I'm trying to determine if the following two functions are inverses of each other. In order for them to be inverses, I know that f of g of x must be equal to x. So I'm going to evaluate f of g of x, and hopefully at the end I'll get that f of g of x is equal to x. So f of g of x is equal to f of the expression that g of x is equal to, which in this case is x minus 2 over 3. Notice I took out g of x and I replaced it with its function. Now I would like to do f of this function, f of x minus 2 over 3. So I know that the f function says 3 times x plus 2. But instead of x, I'm going to replace x with the expression x minus 2 over 3. Then I'm going to reduce. The 3's divide out. I'm left with x minus 2 plus 2, or x. So therefore, f of g of x is equal to x. So a lot of students will stop right here and say, yay, f and g are inverses. But you've only satisfied the first condition. In order to show that they're inverses of each other, both conditions have to be verified. Therefore, I now have to find g of f of x and make sure that this also does equal x. So we have g of f of x, but f of x can be replaced with the expression 3x plus 2. Now I would like to find g of the expression 3x plus 2. The g function says x minus 2 over 3. But instead of x, I'm going to substitute 3x plus 2 in for x. Now I would like to simplify or reduce. In the numerator, plus 2 minus 2 add to 0, and I'm left with 3x over 3, or just x. So g of f of x does equal x. I have now shown both cases, and now I can say f and g are inverses. Take a look at the next function. I have f of x equals 1/4 x minus 5 and g of x equals 4x minus 20. And I'm asking myself the same question. Are these functions inverses or not? So I'm going to find f of g of x, which is the first condition, which is f of the expression 4x minus 20. I'm taking out g of x and replacing it with his expression. Now I want to take the 4x minus 20 expression and substitute it into the f function. My f function says 1/4 x minus 5, but instead of x, I'm replacing x with 4x minus 20 from the inside of my parentheses. Next, I'd like to reduce, and when I distribute, 1/4 of 4 is x, 1/4 of 20 is negative 5, minus 5, and so therefore f of g of x is equal to x minus 10. Notice the minus 5 don't add to 0. They do not cancel each other out. So we have x minus 10. Does f of g of x equal x? Well, no, it doesn't at all. So I can stop here. I don't even have to do the second half of the problem because I already know that f and g are not inverses. They can't be inverses because f of g of x does not equal x. On the last problem here, I'd like to evaluate f of g of x again in order to find out if these two functions are inverses. So we have f of 2 over x plus 5. Now I'm taking the expression 2 over x plus 5 and substituting it into the function f. The function f says 2 over x minus 5. But instead of x, I'm going to substitute in 2 over x plus 5. And now I would like to simplify. Plus 5 minus 5 add to 0. And I'm left with 2 over x. And 2 over 1 divided by 2 over x, that's the same as multiply by its reciprocal. The 2's divide out, and I'm left with just x. So therefore I know f of g of x does equal x. So I'm half done. All I need to do now is verify the second condition that says g of f of x is equal to x. So I'm going to evaluate g of f, and in this case f is 2 over x minus 5. Now I'm taking the expression 2 over x minus 5 and substituting it into g. In this case, g's function says 2 over x plus 5. But instead of x, I substitute in 2 over x minus 5. On the fraction, I know that the numerator is 2, or 2 over 1, multiplied by the reciprocal of the denominator, x minus 5 over 2. And now the 2's divide out, I'm left with x minus 5 plus 5, or just x. And I know that g of f of x is equal to x. And this is really good news for us, because if f of g of x is equal to x and g of f of x is equal to x, I know that these two functions f and g are inverses because they satisfy the two conditions. The next type of problem that you'll be asked to do is to find an inverse from an equation, given that the function is 1-to-1. So in this case, I'm only giving you one function, which I've already told you is 1-to-1. Because this function, I'm only giving you one, I can't use the definition above. In the definition above, I used two functions to verify if they are inverses or not. I was trying to find out if they were, determine. In this case, I'm only given one function, and I'm asked to find the other function. Well, I clearly can't use the same method because I don't have two functions to find the inverse of. So before we look at the steps to find an inverse from an equation, I want you to look at this note over here. We have this new notation that looks like f of x, but with this little -1 up here. This is a notation for the inverse of f of x. The way we pronounce this notation is f inverse of x. Notice that this little -1 up here is not an exponent. It is not to be read f to the -1 exponent. That is not how we pronounce the inverse function. This is just a notation saying, hi, I'm the inverse of f. That's what this little f and the -1 up here means. It does not mean a -1 exponent. It means f inverse. So let's look at our steps. The first step says change f of x into y, so it's easier for us to manipulate. The second step is our real true inverse step. I'm switching all my x values with all my y values. Every time I see an x, I plug in a y. Every time I see a y, I plug in an x. I'm switching all x and y values. And this is really our inverse step because this is where my domain of my function is being interchanged with the range of the inverse. Similarly, my range of my f is being interchanged with my domain of its inverse. I'm switching all x's and y's, which switches all the inputs and the outputs, which creates a new equation, and the equation is now an inverse. Next, I'd like you to solve for y to make the equation a little bit prettier and change the y back into f of x. We're the one that put y into the problem, so at the end we have to take it out. So let's take a look at this first problem. My first step says take my function f of x and change the f of x to y. My second step says to switch all x's and y's. So when I see a y, I'm going to plug in an x. When I see an x, I'm going to plug in a y. All x's and y's are interchanged. Notice that the blue equation is not equivalent to the green equation. When I did my step 2, I've changed the entire equation around. This is not an equivalent step. Usually in math, the first line is equivalent to the second line, but in this case, I'm actually changing the entire equation from the purple f of x to his inverse in green. Now, even though this is an inverse, it's not written very pretty, so step 3 says we're going to solve for y. So I'm going to subtract 7 from both sides and divide by 2 to get y equals x over 2 minus 7 over 2. My fourth step says change my y back to f inverse of x. Notice the problem was given to me as in function notation, so I need to give my answer back in function notation. Although this is not the same function, it's the inverse function. So I write f inverse of x is equal to x over 2 minus 7 over 2. I could also write the same function x minus 7 all over 2. Both of these answers are acceptable. Looking at our next problem, my first step says to take my function and take out the f of x and replace it with y. Now that I've replaced f of x with y, I'm going to interchange all my x and my y values. This is creating a new function, and this green function is the inverse function, although it's just not written very pretty. So we're going to solve for y to make it look a little bit nicer, so we can put it in function notation. I'm going to add 1 to both sides. Next, I'm going to divide all terms by 4. And lastly, I need to take the cube root of both sides to get y all by itself. So I'm left with y equals the cube root of x over 4 plus 1 over 4. So I've solved for y, but now I need to answer my question in function notation. So f inverse of x is equal to the cube root of x over 4 plus 1 over 4. Another acceptable answer would look like f inverse of x is equal to the cube root of x plus 1 all over 4 if you wanted to combine the two terms to one denominator. Both are acceptable. For my last problem, I have f of x is equal to 2 over x, and I'm still trying to find the inverse. First, I take out f of x and replace it with y. Next, I interchange all of the x's and the y's, creating a new function, an inverse function. And to solve for y, I'm going to cross multiply here. I have xy is equal to 1 times 2, or 2. To solve for y, I'm going to divide by x, and y equals 2 over x. Now that I've solved for y, I'm putting my answer in function notation, step 4. F inverse of x is equal to 2 over x. And that's my answer. Now this one's actually a very interesting function because the function f of x is 2 over x happens to be his own inverse, and that's just pretty amazing. Most of the functions have a much different looking inverse function, but in this one function, the function happened to be its inverse function, and that's just cool. The last thing we need to do is to learn how to sketch an inverse from a graph. So if I gave you y equals x squared, and I'm trying to get some points, I can plug in -2 until 2. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So this is my graph of x squared. Is this original graph a function? Well, yes, it passes the vertical line test. Is this original graph 1 to 1? Well, no, it's not. What if I was trying to graph his inverse? The definition of an inverse says that the x values, or the domain, become the y values, or the range, in the inverse. The y values in the range become the x values in the domain of the inverse. So instead of the point -2, 4, I'm getting 4, -2. And 1, -1 all the way down. Interchange your x and your y values, which is exactly the same step that we did in the previous question where we were asked to find an inverse from an equation. We had to switch all x and y values because that's the definition of an inverse. The domain and the range interchange places. So if I want to graph this inverse, I plot the points and then let's answer the question, is the inverse graph a function? Well, no, this inverse graph is not a function because it doesn't pass the vertical line test. So this is no, it's not a function. Well, how come I started off with a function and I did the inverse and I didn't get a function? Why? Well, the answer here, the inverse graph was not a function because the original graph was not 1 to 1. And we said because the original graph is not 1 to 1, therefore we cannot have an inverse function. You can graph the interchanged points, but the inverse will not be a function. So the only time you're ever going to get an inverse function is if the original graph was 1 to 1, which we talked a little bit about earlier. I just like to show you visually why that doesn't work. On this next graph, we have a piecewise graph. Is this graph a function? Well, yes, it is a function because it passes the vertical line test. Is this function 1 to 1? Well, yes, it is because it passes the horizontal line test. So because it's a function and is 1 to 1, I can find his inverse and graph the inverse. Now, I'm not going to find the function. All I'm going to do is to graph the inverse. So first I'd like to take my original graph and get some points. I can see a nice point right here, -3, -1. I see another point at 0, 2. I see another point at 6, 4. And if you really want, we could do one more right there at 3, 3. Now I'm going to try to graph the inverse. In order to graph the inverse, I'm going to use the step where I interchange my x and my y. My domain becomes my range, and my range becomes my domain. So I have -1, -3, 2, 0, 3, 3, and 4, 6. When I plot these points, -1, -3, 2, 0, 3, 3 lands right on the other graph, and then 4, 6. And I can connect these points, and I get the inverse graph. One interesting thing to note is that if you draw the line y equals x, the original graph is a reflection of the inverse graph over the line y equals x. And that's because are interchanging x and y, so it's reflecting over the graph y equals x because the two lines are interchanging. On my last graph, first thing I'd like to identify is it a function? Well, sure, it is a function. It does pass the vertical line test. Is this function 1 to 1? Well, yes, it is 1 to 1 because it passes the horizontal line test. Next, I need a few points for my original graph. So I find some nice points that are easy to identify. -3, -1, 0, 0, and 3, 1. I note that these do have arrows, so they do keep going above and below the points that I have here. To find the inverse, I'm going to take the x and the y values and interchange them. So instead of -3, -1, I'm getting -1, -3. Instead of 0, 0, I'm getting 0, 0. And instead of 3, 1, I'm going to plot 1, 3. When I plot these 3 points, I know that I need to connect them with a straight line with arrows because they do keep on going. I just grabbed 3 of the points. So I connect them with arrows. It is interesting to note here that if you plot the line y equals x, the inverse would be a reflection of the original graph. That concludes our discussion on inverse functions. You are now able to verify if 2 functions are inverses. If I give you one function that is one-to-one, you're able to find its inverse, and lastly, you're able to sketch an inverse from its graph.